Hello, and welcome to a lecture video on some matrix algebra prerequisites before we begin Chapter 8. So in this video, we won't be doing any differential equations. Instead, we'll be learning what matrix multiplication is and what eigenvalues and eigenvectors are. And this will be some matrix algebra that will be imperative in Chapter 8. So matrices can arise as a useful tool in solving systems of linear equations. First, though, before we do that, let's discuss the elimination algorithm, and then we'll see how to do this with matrices. So the elimination algorithm is a method for solving a system of equations that operates by eliminating components of an equation in such a manner that in the end, what we're left with is just x is something, y is something, and z is something. So obviously, after we eliminate, these numbers will probably be different. And this elimination will occur in the following way. We'll first eliminate this 2x. And then we'll eliminate that guy. Then we'll eliminate this. Then we'll eliminate this if it existed. And you can see the pattern. We proceed in a counterclockwise motion, eliminating each of these. And then in the end, after all of those are gone, so this is the elimination order. After those are gone, then we'll just have x is something because there's nothing else, y is something, and z is something, whatever those numbers are after we eliminate. And how do we eliminate? Well, we can add a multiple of one equation to another, just like we have been doing for a long time to solve two equations, two unknowns. And we always eliminate using the entry, the corresponding entry of the main diagonal. And by the main diagonal, we mean this diagonal here, this xyz, this main diagonal from top left to right bottom. So to eliminate that 2x, in other words, we want to use this x up here. And our step 1 would be to do equation 2 minus 2 times equation 1. And that will convert the system into the following. So equation 1 remains unchanged. We're not actually doing anything to it. Instead, we're just using equation 1 and subtracting 2 times equation 1 from equation 2. So to be clear, this step looks like this. We are subtracting 2 times the first equation from the second. And then we have 2x minus 2x goes away. That's the point. Y minus 6y is minus 5y. 0 minus negative 4z is positive 4z. And 4 minus 2 times 1 is 2. So after we do that first elimination, our system looks like this. And the third equation we haven't touched yet. So at each of these steps, that's what we mean by eliminating. And we do it in that way, always using the entry of the main diagonal, adding or subtracting the main diagonal from the equation that we want to modify in such a manner as to eliminate the thing that we want to eliminate. In this case, to eliminate the 2x, we had to subtract that x. So we did this. And then we can continue. So now we move on to step 2. Now equations 1 and 2 are unchanged, and we're going to be modifying equation 3. Okay, so we want to get rid of that x, and we always want to use the entry of the main diagonal above or below it. So in this case, it's using that x there. So how can we get rid of that x using that x? Well, a simple subtraction. So we can do equation 3, simply minus equation 1, no need to scale it. So doing that subtraction, we have an x minus x goes away is the point, minus y minus 3y is minus 4y, z minus negative 2z is 3z, and 2 minus 1 is 1. So that completes steps 1 and 2. And by the way, my writing this out, those are just to make perfectly clear what we're doing. I will no longer be writing these out. I'll just say something like equation 2 minus 2 times equation 1, and then you need to do the mental arithmetic, which is just subtracting coefficients. Okay, so now we move on to step 3. And this is where we might need to do something other than a simple adding a scalar multiple, because we have, unfortunately, a minus 4y and a minus 5y. So we could do something like scale this by 4/5 to make that 5 into a 4, but then we have horrible fractions and we don't want to deal with that. Can you think of any way that we can change these two equations to begin with, maybe some scaling, so that then we can eliminate this guy without having to deal with fractions? So here's what we had. And if you thought of the least common multiple, then that's a fantastic idea for avoiding fractions. We can take this equation here, and we'll multiply both sides by 4, and take this equation here and multiply both sides by 5. And we can multiply both sides of an equation by a number that's doing the same thing to both sides, perfectly fine. So this is just a nice intermediary step in order to avoid fractions. So doing these two operations, we have this. And now that we've multiplied equation 2 by 4 and multiplied equation 3 by 5, now we can just do a simple subtraction, and we can complete step 3. So now we'll do equation 3 minus equation 2. And when we do that, we'll have 20y minus 20y goes away, eliminating this just like we want. So equation 3 minus equation 2, those go away. 15z minus 16z is negative z, and 5 minus 8 is minus 3. And you can see that now we've solved for z, because taking this last equation and just multiplying both sides by minus 1, z is 3. So this is what your system looks like after you complete steps 1, 2, and 3. And I should note that something I did omit is that we also want to make it so that each of these center terms is in the end just by itself, because that's the whole point, to isolate them. And now we can proceed to step 4. Notice that initially there was nothing here, but in the process of doing steps 1, 2, and 3, we introduced a term there. Now it's a 16. So we do in fact need to do step 4, and we always do these steps with the system that we have at the time, because if we were to use one of the original equations, then we might reintroduce an x back here, for example, and we don't want to do that. We want to keep the guys that we've eliminated. So that was step 3. Now we do step 4. And in step 4, how can we eliminate that 16z? And what do we eliminate it with? Remember that we always eliminate using the element of the main diagonal above or below it. So we will eliminate that 16z, not using that z there. No. If we use this z here, we'll reintroduce an x down there. We do not want that. We'll eliminate this z using that z there, because that is the z in the main diagonal above or below that thing that we want to eliminate. This z up there is not in the main diagonal. So using this z, which is this z here, we will do equation 2 minus 16 times equation 3. Then it's 16z minus 16z goes away. So equation 2 minus 16 times equation 3 yields the following. Equation 1 is unchanged. Equation 2 becomes that. And equation 3 is that. And you can see that now y is just about by itself. Now we'll just divide both sides of this equation 2 by negative 20, and y will be 2. So this is what we had. We completed steps 1, 2, 3, and 4. And then we divided both sides of equation 2 by negative 20 to isolate y. And now we want to eliminate this guy. That's our step 5. And we eliminate using the enter of the main diagonal, which is that z. We have a minus 2z. To get rid of that, we'll add 2z to it. So we'll do equation 1 plus 2 times equation 3. Okay, now we have x plus nothing is x, 3y plus nothing is 3y. Minus 2z plus 2z goes away is the point, and 1 plus 2 times 3 is 7. And now very last, we eliminate this 3y using the entry of the main diagonal, which is that y. So we will do equation 1 minus 3 times equation 2. And those go away, and 7 minus 3 times 2 is 1. And we are done. So now we have it in our nice form of just a nice diagonal x, y, z with the values of each on the other side. So that is the elimination algorithm, as it's called. And it works always in this order. You eliminate moving counterclockwise. And sometimes we want to do some intermediary steps to avoid fractions, like scaling an equation by a number on both sides, which is just multiplying both sides of that equation by a number, like we did in that step before we did step 3. Now, this is great, but notice that all we ever did in each step was really just add and subtract coefficients. I mean, in a sense, it was kind of redundant having to write a y in this position every time, when the second position was always just the y position. So this is our introduction to matrices, and we can write what is called the augmented matrix for this system, which looks like this. It contains the coefficients in the coefficient matrix, as we call it. And then we typically denote the equal sign with a vertical line. Not all sources use this custom, but I will be using it. So we can read across a row. That's the x column, that's the y column, that's the z column. And reading across this first row, that's 1 times x plus 3 times y minus 2 times z equals 1, which is the first equation. The second row is 2x plus 1y plus 0z equals 4, which is the second equation. And then what we can do is do the elimination algorithm on this augmented matrix instead. So it works exactly the same way. We can do row addition and scaling, etc., because each row fundamentally is just an equation. It's just kind of a shorthand way of writing the equation. So we'll eliminate in the same order as before, which was this order. And all of the arithmetic is literally exactly the same. It's just that now we're adding and subtracting rows instead of equations, but each row is an equation. So for example, in step 1, we want to eliminate that 2, and we always eliminate using the entry of the main diagonal above or below the thing that we want to eliminate. In this case, it's that 1 right there. We want to eliminate that 2 using that 1. We will do row 2 minus 2 times row 1. That means that row 1 stayed the same, and also row 3 stayed the same. And the only thing that we're doing is taking row 2, which was 2, 1, 0, 4, and subtracting 2 times row 1, which was 1, 3, minus 2, 1. And doing that subtraction, we have 2 minus 2 times 1. By the way, I should say that when we subtract a row, that means that we subtract each corresponding entry, and we distribute that minus 2 to all components. So 2 minus 2 times 1 is a 0 there. 1 minus 2 times 3 is 1 minus 6, is a negative 5 there. 0 minus 2 times minus 2 is 0 plus 4 is 4. And here we have a 4 minus 2 times 1 is 2. So that's where this 0, minus 5, 4, 2 comes from. Now this should look familiar, and we can always read off a augmented matrix for the system of equations that it is. So reading this off with our knowledge that this is the x, y, and z columns, and this is the constant column. This is x plus 3y minus 2z equals 1. It's 0x minus 5y plus 4z equals 2. And 1x minus 1y plus 1z equals 2. And notice that this is exactly what we had before after we finished step 1. And what we did here is step 1. It's just that we did it with a matrix instead of writing out the x's, y's, and z's in each column. And then we would move on to step 2, same as before, and we do it in exactly the same way. So now we do that step 2 elimination. Before we did equation 3 minus equation 1. In the same way here, we'll do row 3 minus row 1. So here's the matrix we had. And now we move on to step 2, eliminating that 1 right there. And we can do that by doing row 3 minus row 1. And subtracting rows is just subtracting the corresponding entries. Okay, so rows 1 and 2 are unchanged. We're only modifying row 3. 1 minus 1 is 0. Minus 1 minus 3 is minus 4. 1 minus negative 2 is 3. 2 minus 1 is 1. And that achieved our goal of getting a 0 there. Now, why is this valid anyway? Why can we just subtract one row from another? Well, remember that each row is an equation. And just as we can subtract one equation from another, and when we subtract an equation from another, we subtract the corresponding x's, the corresponding y's, the corresponding z's, that amounts to just adding or subtracting the corresponding coefficients. So that 1 minus 1 is the same as x minus x going away. The minus 1 minus 3 is the same as negative y, negative 3y, becoming a negative 4y. That 1 minus negative 2 is actually z minus negative 2z is 3z. Yep, so just keep in mind that rows are equations, and you're really just adding and subtracting equations, and that's why all of this is valid. So this should also look familiar. It's what we had after finishing steps 1 and 2, and now we can continue. We can take a row and multiply the entire row by a scalar, just like we did before. We multiplied this by 4, and we multiplied that by 5, and by that we mean the whole row. And that's valid because it's the same thing as taking an equation and multiplying it by 4 on both sides, or by 5 on both sides. Okay, so negative 5 times 4 is 20, 4 times 4 is 16, and 2 times 4 is 8. And then this row we're multiplying by 5. 3 times 5 is 15, and we have that. And we're doing that so that then when we do our step 3, now it's that simple subtraction, row 3 minus row 2, just like we did before with equation 3 minus equation 2. And remember that we can stop and read off what a row is saying at any time. So this third row is saying 0x plus 0y minus 1z minus e equals minus 3. So this is the same set of equations that we had when we were doing it without the matrices, and it will continue to be the same at every step. And now what did we do here? We solved for z here by multiplying both sides by minus 1, which is the same thing as multiplying row 3 by minus 1, and getting that. And then we proceeded with step 4 by eliminating this guy now. And what is our goal? Well, what we want is a nice diagonal of 1s with nothing else there, and then some numbers here. Because if we were to read this off, then this first row would say 1x plus 0y plus 0z equals something. So that first row would be saying x equals whatever that is. The asterisk is a placeholder for whatever is there. The second row would be saying that y equals whatever that is. And the third row is saying that z equals whatever that is. So with a matrix, then we're going around counterclockwise just as we were before, and we're making everything else zeros, except in the diagonal, which we're making 1s, and we always use the element of the main diagonal to eliminate and make the things below it and above it zeros in this counterclockwise order. Okay, so now from this, what was our step 4? We want to eliminate that 16 using not that minus 2, that's not in the main diagonal. We want to eliminate that 16 using that 1 there. So we'll do row 2 minus 16 times row 3, and we have that. And keeping in mind our end goal of wanting that to be a 1, now that everything else in that row is eliminated, we'll scale row 2 by 1 over negative 20, which just means dividing everything in that row by negative 20, and that will make row 2 look like 0, 1, 0, 2. Okay, and we also want to eliminate that minus 2 there. So let's do step 5. And we eliminated that minus 2 using that 1. So we'll do row 1 plus 2 times row 3. And this minus 2 plus 2 will go away. And we'll have a 1 plus 2 times 3 is a 7 there. And for these entries, we're adding multiples of 0. So those stay a 1 and a 3. Okay, now our matrix here looks almost like a nice diagonal of 1s. And our last step will be this step 6. We want to eliminate that 3, again, using the element of the main diagonal below it. So 3 minus 3 would go away. So we want row 1 minus 3 times row 2, because then it's 3 minus 3 times 1 will go away. So row 2 and row 3, we're not changing. And now row 1 will be 1 minus 3 times 0 is 1. 3 minus 3 times 1 is 0, is the point. 0 minus 3 times 0 is 0. And 7 minus 3 times 2 is 7 minus 6 is 1. And when we have this nice diagonal of 1s, then that means that we're done. This is the solved system. And we can now write out what each equation is saying. So this first equation is saying that x plus 0 is 1. The second equation is saying 0 plus y plus 0 is 2. And the third equation is saying that 0x plus 0y plus z is 3. So that is the elimination algorithm, both without and now with matrices. And with matrices, we had some fundamental row operations that we were doing, like we could add a multiple of one row to another, or we could take a row and scale that entire row by a constant, which is the same as multiplying both sides of the equation by that constant. So like here, when we took row 2 and we divided everything in row 2 by -20 to get it to look like that, that was another fundamental row operation, as we call it. And the elementary row operations are adding a multiple of one row to another. This is the one that we were doing the most. Scaling a row by a non-zero constant. We did this a couple of times. And swapping two rows. We did not do this, but swapping two rows is the same thing as just writing the equations in a different order, since each row is an equation. So that's why that's also a valid thing to do. So if you're given an augmented matrix, you can do a sequence of elementary row operations, and the result that you get will have the same set of solutions as the original, because all of these are valid things to do. It's adding a multiple of one equation to another, multiplying both sides of an equation by a constant, and just rewriting it so that your equations are in a different order. And if one matrix A can be transformed into another matrix B through a sequence of elementary row operations, then A and B are said to be row equivalent. Sometimes we denote that with a little tilde between them. So in the example that we just worked through, all of those matrices that we were writing down, every single one was row equivalent because each of them was obtained through doing elementary row operations to the previous one. So that's our example. Every matrix we just wrote down, they were all row equivalent to each other. Now, we can scale matrices and add them together. And scaling a matrix by a constant s just means multiplying every entry in the matrix by that constant. So for example, 3 times this matrix, we just multiply every entry in there by 3, and that would be 3, 6 minus 6, 9. And if two matrices are of the same size, we can also add them together. And adding two matrices together is adding together the corresponding entries in A and B. So for example, this matrix plus that matrix, all we do is we add together the corresponding entries. So 1 plus 2 results in a 3. Similarly, 2 plus 5 results in a 7, and so forth. And if the matrices are not of the same size, so for example, if we try to add 1, 2 minus 2, 3, and this matrix, then this just does not exist because they have mismatched dimensions. And speaking of dimensions, what do we mean when we say that a matrix is n by m? When we say that a matrix is n by m, it's the number of rows by the number of columns, which is the same thing as height by width. So, for example, this matrix is a 3 by 2 matrix. It has 3 rows and 2 columns. It's rows by columns, which is height by width. Matrix subtraction works exactly the same way. It's subtracting the corresponding entries. So subtracting the corresponding entries, 1 minus 4 is minus 3, and so on. So that's matrix scaling and addition. And we can also multiply matrices. And unlike scaling and addition, multiplication is not a straightforward thing. It's not just the product of the corresponding entries. Before we talk about the general case of matrix multiplication, we need to talk about the n by 1 case. So given an n by 1 matrix, X, and n by 1, remember that's height by width, so this is n rows and 1 column. And an n by 1 matrix is also called a vector. And given an m by n matrix A with columns b1, b2, and so on, and an n by 1 matrix X with entries x1 to xn, then the product AX is x1, b1 plus x2, b2, and so on. So for example, if this is our A times X, what this is saying is we have columns b1 and b2, and this product is x1, b1, plus x2 b2. So that's minus 1 times 1, 3, plus 2 times 2, 4. And this is matrix scaling each of these. So the minus 1 times this matrix, we distribute it to each component. So that's minus 1 minus 3. And similarly, we distribute the 2 to each component. So 2 times 2 is 4, 2 times 4 is 8. And adding those, we have 3, 5 is the result of that matrix product. So matrix multiplication, the guys inside X are what we call the weights on the columns of A. It tells us how far in the B1 direction we go, plus how far in the B2 direction we go. Kind of like a coordinate system. And under this definition of matrix multiplication, a matrix is like a function that accepts a vector and outputs another vector. And in fact, that's exactly how we want to think about it. It turns out that matrix multiplication is linear, and it is a linear function. And what we want to be able to do is to compose functions. So if I feed -1, 2 into this function, it outputs 3, 5, and then we might want to take that output and feed it into some other function, some other matrix. And function composition, we should be able to compose two functions, and we want to define matrix multiplication in such a manner that matrix multiplication is function composition. And there is one and only one way to do that, and it is this. The general case for matrix multiplication is that given an m by n matrix A and another matrix B with columns B1 to Bk, then the matrix product A times B has columns AB1, AB2, and so on. So, for example, if we were to take the product of these two matrices, the meaning of this is that we do what we did before, except twice. So this is our matrix A here, and these are our B1 and B2. And what we do is we compute AB1 and AB2 separately, and we stick them as the columns here. So AB1, that would be 1, 2, minus 2, 3, times minus 1, 2, and we compute that. Remember that these are just the weights on the two columns, so it's minus 1 times the first column, minus 1 times the first column, plus 2 times the second column of the matrix, which is 2, 3. And we compute that, and we have minus 1 plus 4 is 3, and 2 plus 6 is 8. And that 3, 8, that was our AB1, so it is the first column of the matrix product. And then here, we'll do the same thing, but with AB2, and stick the result there. So AB2 is this product. So 3 times the first column plus 1 times the second column. So we have a 3 times 1 plus 1 times 2 is 5 up there, and a 3 times minus 2 plus 1 times 3 is minus 3. So that is the matrix product of these two. And again, this is function composition, really, because each of these matrices can accept an input and give an output. And this is the matrix where if we were to feed a vector into it on the right, not via matrix multiplication, it's the same thing as first feeding it into this matrix and then taking the output of that and feeding it into this one. So this is the matrix that composes the actions done by these two matrices all in one fell swoop. Now, since we'll be doing matrix multiplication a fair deal, I'll show you how I always think of it computationally. So we had been doing it like this, and this comes from the direct definition. However, we could also think of it this way. So when I see a matrix product like this, what happens in my mind is I imagine taking the minus 2, 1 and tilting it sideways over the matrix like this, and sort of sprinkling down the entries. So we have a minus 1 there and minus 1 there now, and doing a multiplication and sprinkling down the entries under multiplication and adding together the results. So again, what happens kind of visually in my mind is I take this minus 1, 2, I tilt it sideways over the matrix like this and sprinkle down the result. The sprinkling is multiplication, and then I add together across. And this sum is -1 plus 4 is 3, and 2 plus 6 is 8. Accomplishing, of course, the same thing. What's happening arithmetically is identical. This is just a kind of shorthand way to do the computation. Now, under matrix multiplication, there is such a thing as the identity matrix. The identity matrix is a diagonal of ones in which everything else is 0. And it is called the identity matrix because it is the only matrix such that IA is A for any matrix A. So in other words, multiplying by I keeps the matrix the same, hence identity. It's like the number 1. So for example, if we take the 2x2 identity matrix and multiply it by a matrix, then you can compute that the result is the same. So IA equals A, because when we tilt and sprinkle, we'll just end up recovering each of the 2 columns. And when I say tilt and sprinkle, I'm referring to this technique for quickly doing matrix multiplication. I encourage you to pause the video and do this method for computing this matrix product. You would tilt and sprinkle the first column here over this matrix. That would be the 1 minus 2, then tilt and sprinkle the 2, 3 over this matrix, and you'll get a 2, 3 again. So IA is equal to A, no matter what the matrix A is, in the same way that 1 times a number is that number times 1 is that number. So the identity matrix is to matrix algebra what the number 1 is to arithmetic. And given an n by n matrix A, the inverse of A, denoted A inverse like this, is the unique B such that AB is equal to I. And you can think of this as like the reciprocal. So 5 to the power of -1 is 1 over 5. And if you multiply any number by its reciprocal, so 5 times the reciprocal of 5 is equal to 1. So that's one analogy for it. Or it's the same as how f of f inverse of x is equal to x. If you compose any function with its inverse, you end up getting the identity function that just maps x to x. And that identity function that just maps an input to itself is the identity matrix. After all, the identity matrix, it maps 1, -2 to 1, -2. It is the identity function as well. So both of these are fine analogies for thinking about what the matrix inverse is. It's like the reciprocal, it's the function inverse. So here's a 3x3 example. The inverse of this matrix is that, and we can verify by multiplying them and seeing that it's the identity matrix. So if we take these 2 matrices and multiply them together, then what do we get? Okay, well, so this is our column B1, B2, B3. This whole thing is our matrix A. So what's AB1? Well, it's that. And using our tilt and sprinkle, we'll take that 1, 0, 1, tilt it over. The sprinkling down is products, and we'll add together across. So that matrix product looks like this. And computing, we have 1, 0, and 0. So our first column here is 1, 0, 0 due to that. And one can compute the others similarly. This column here, that would be AB2. This column here, that would be AB3. And one would end up getting 0, 1, 0, and 0, 0, 1, which is the identity matrix, and that confirms it. Why do we care about matrix inverses? So consider a linear system, a system of linear equations like this. We can always write a system of linear equations as a matrix equation in the following way. And matrix equations are really what we're building up to and what we'll be using to deal with differential equations. We can stick brackets on both sides, like this. And now it looks like, on the left, a sprinkle and add has been done. That is the same as 2, 5, 1, 2 times x, y. And this is a matrix equation. It is of the form AX equals B. So where we let capital X be the unknown matrix XY, and A be this 2 by 2 matrix and B be 2, 3, this is AX equals B. So any system of linear equations is equivalent to a matrix equation and vice versa. And we will be able to solve this with the following clever technique. If we can find the inverse matrix to A, then what we can do is multiply both sides by A inverse. So multiplying both sides by A inverse on the left, it looks like that. But what is A inverse times A? Well, A inverse times A is I, the identity matrix. But what is the identity matrix times any other? Well, it acts like the number 1. It doesn't change it. So through a relatively straightforward computation of A inverse times B, we actually have the solution for what x and y are. Capital X, which is x, y, is this product. We'll now see how to find matrix inverses, at least for the 2 by 2 case, and then we'll illustrate this with actual numbers. We'll come back and solve this and see it in application. So it is a theorem that the inverse of a matrix ABCD is 1 over AD minus BC times this matrix. And the way I always think of this is it's like the A and D get swapped, and we stick minus signs by the B and C. And then we divide by this guy, known as the determinant. And that determinant is the AD minus BC. So it's kind of the main diagonal minus the other diagonal. So again, what happens in my mind is writing it down, 1 over AD minus BC, and then the A and D get swapped, and we stick minus signs by the B and C. And if the determinant is 0, then we're dividing by 0, so the inverse doesn't exist. Not every matrix is invertible. So for example, what's the inverse of this matrix? Well, it's 1 over AD minus BC, 1 over 1 times 5 minus 2 times 3, times, so we swap the main diagonal, swap the 5 and 1, and stick minus signs by the others. We compute that guy outside. 5 minus 6 is minus 1. 1 over minus 1 is just minus 1. So we have negative 5 minus 2 minus 3, 1. And the minus sign, this is matrix scaling, it distributes to all components inside the matrix. So that is negative 5, 2, 3, negative 1. Is the inverse of that matrix, and you can always check your work by taking the product and making sure you get the identity, the same way that we verified the 3 by 3 case earlier. So for example here, we could solve this in this described way, and A inverse, we would find the inverse of 2, 5, 1, 2. And what is the inverse of 2, 5, 1, 2? Well, it's 1 over AD minus BC, and we swap the main diagonal and stick minus signs by the other, and we compute that this is the inverse matrix. So we can quickly solve for xy by multiplying both sides by the inverse. So multiplying both sides of this on the left by the inverse, A inverse A goes away, and we have that x is just A inverse B, and A inverse is negative 2, 5, 1 minus 2, and B is still 2, 3. And remember that capital X, that was just shorthand for xy. So we have that xy is this product. Let's compute that. We'll tilt and sprinkle the 2, 3 with products and addition, like such. And the result is negative 4 plus 15 is 11, and 2 minus 6 is minus 4. And that was our x and y. So what we have found is that x equals 11 and y equals negative 4 is the solution to the system of linear equations that we began with over here. And you can plug in and verify. Indeed, 22 minus 20 is 2, and 11 minus 8 is 3. So that's quite quick and great, and a nice utility of the inverse matrix, and matrix multiplication. Okay, now, for where we're going with this, we need to be able to also solve systems with multiple solutions. So consider the following augmented matrix. Remember that this corresponds to the following system of equations. We can read off each row, and it is solving that system of equations. Now, a system of linear equations can have many, one, or no solution. A simple example of a system with no solutions would be x plus y is 1 and x plus y is 2. Well, x plus y can't be both 1 and 2 at the same time, so this has no solution. If we were to try to solve this by, say, subtracting the second equation from the first via elimination, we would get 0 is -1, a contradiction. And if you get a contradiction, that tells you that there is no solution. In the same way, we can have infinitely many solutions. So for example, x plus y is 1, and also 2x plus 2y is 2. So you can see that these two equations are the same thing. We just took the first equation and multiplied it by 2 on both sides. And if we say subtract 1/2 of the second equation from the first, then we'll get 0 equals 0. And what that means is that there are infinitely many solutions. And again, over here, this means that there are no solutions. So both of those situations can happen. However, in the case of infinitely many solutions, that doesn't mean that every single pair xy is a solution. This is a line. X plus y equals 1 is a line, and the solutions are only those that lie along the line x plus y equals 1. And what we want is a way of finding all solutions and parameterizing all solutions in a nice way. So let's solve this system, and we can solve this in the same way with the same elimination algorithm that we had before, except that if it has infinitely many solutions, then something like this will happen along one of the rows, but that won't be too big of an impediment. We'll see what we do about it. Okay, so we want a 1 in the upper left. So we could divide row 1 by -4, but then we'll have fractions. So instead, let's swap rows 1 and 2. Remember that these are our elementary row operations. Each row is an equation, and we can add a multiple of one row, one equation to another. We can scale a row by a non-zero constant. That one is multiplying both sides of the equation by a non-zero constant. And we can swap two rows, which is the same as just swapping two equations, writing the same equations in a different order. So to avoid fractions, let's swap row 1 and 2. Okay, we've swapped those first two rows. And the reason that we're doing that is now, since we want to get a 1 in the upper left, remember we want like a nice diagonal of 1s ideally, we can take row 1 and divide it by -2. And now row 1 is 1, 2, 1, dividing each element of row 1 by -2. And while we're at it, let's also divide row 3 by 2. So taking row 3 and dividing it by 2, we have 1 minus 1 and -2. Now remember our elimination order. We want to eliminate this, and we always eliminate using the element of the main diagonal. So we want to use this 1 there to eliminate the -4. Let's do row 2 plus 4 times row 1. Okay, so rows 1 and 3 stay unchanged by this. And row 2 plus 4 times row 1, we have -4 plus 4 goes away, is the point, eliminating it. -2 plus 8 is 6, and 2 plus 4 is 6. Okay, and we want a 1 in that 6's position anyway. So let's take row 2 and divide it by 6. And now we move on to our next elimination target, which is this. Let's eliminate that. And we can do that by doing row 3 minus row 1. We always eliminate using the element of the main diagonal. And doing that, we have this. And now we move on to the next stage, which is eliminating that. And we want to eliminate that using this 1 right there in the main diagonal. But you may notice what happens after we do that elimination. Well, this whole row will become 0. Let's continue this on the next slide. Okay, so we had this matrix. And remember that we can read off the rows. So this first row says x plus 2y plus z is 0. The second row says y plus z is 0. And the third row says minus 3y minus 3z is 0. And notice that this equation, y plus z is 0, and the third equation are the same equation. We've just taken the second equation and multiplied it by -3 on both sides. So in a sense, the three equations that we began with over here are redundant. One of them was redundant with the other two. So in a certain sense, it was a system of two equations and three unknowns. And we're now discovering that. And as we eliminate this, and we would eliminate that by doing row 3 plus 3 times row 2, since we always eliminate using the element of the main diagonal, so 1 times 3 plus -3 goes away, then that third row is 0, corresponding to the equation 0 equals 0. I'll write that out. This third row here says 0 equals 0, which is no information. And that's perfectly fine. It just means that we eliminated that equation as redundant, since it's a duplicate of that equation. So we're left with only these two equations left. Okay, but how do we proceed from here, and how do we get the full solution set from this? So this is where the part where it differs from the standard elimination algorithm that we learned earlier, which is that at this point, we can't eliminate that one there or that one there. We can't eliminate either of those because there's no element of the main diagonal that we can use to eliminate it. Instead, we eliminate this. Next, we want to eliminate above and below the leading non-zero entries, where the leading non-zero entries would refer to that and that. Leading as in leading in each row, so the first non-zero entry in each row. These guys are called pivot positions. I'll avoid using that term. I'll instead just say leading non-zero entry since it describes what we're talking about in the sentence. So we've eliminated below this leading non-zero entry. And at this point, we've eliminated below this non-zero entry. And there is no leading non-zero entry in the third row, since that's 0. So now, as we continue our counterclockwise motion of elimination with the elimination algorithm, we have to pass over these two, and now we are eliminating above this leading non-zero entry. So we want to eliminate that 2 now, again, always using that leading non-zero entry in the main diagonal. So at this point, eliminating that 2 with that 1, that's row 1 minus 2 times row 2. So now our matrix looks like this. And at this stage, we are actually done. We have finished eliminating above and below the leading non-zero entries. And that's what the elimination algorithm really is. It's eliminating above and below all the leading non-zero entries. Okay, but how do we get from this the general solution? Well, at this stage, once we're done, once we have eliminated above and below all leading non-zero entries like this, we write out the equations. So this first row says x minus z is 0. The second row says y plus z is 0. And the third row says 0 equals 0. This is the same as saying nothing. It's saying that z is free. There is no restriction on what z is. And the thing about eliminating above and below the leading non-zero entries is that we can move the free variable, as we call it, this unbounded z, to the other side of both equation, like this. So this is the same as x is z, and y is negative z, and z can be anything. So we can generate all solutions by letting z be anything, and then we know what the corresponding x and y have to be. But there's more than this. Z being free means that z is z. And this is important to write down. It may not seem like much, but what this allows us to do is we can put brackets around both sides, and we get that the solution matrix, the solution vector xyz, is the same as z negative zz, and then we can pull out the z, so that z times 1 minus 1, 1, and we typically replace that arbitrary variable with a constant like c, and we say that the general solution is c times 1 minus 1, 1. So c is an arbitrary constant, it's a free slider. So what this 1 minus 1, 1 is it is the direction in three-dimensional space. It forms a line, and anywhere in the direction 1 minus 1, 1, any scalar multiple of that, so 2 minus 2, 2, 3 minus 3, 3, any scalar multiple of this vector is a solution to the original system of equations. It will turn out that solving for these underdetermined systems, as they're called, underdetermined in the sense that they have infinitely many solutions, will be very important in solving systems of differential equations. So this will be crucial. And again, you follow the standard elimination algorithm up until the point where you eliminate a row entirely. And then you proceed, except you skip over the pieces where you can't eliminate, because that being a 0 there means you can't eliminate that 1 or that 1. So skipping over, we skip straight to eliminating that 2. And at this point, once we have eliminated above and below all leading non-zero entries, then we write out the system, move the free variable to the other side, and that free variable, we write it as being equal to itself. Then we stick brackets around both sides and pull out the free variable. We often rename the free variable to some other variable letter, just as a matter of custom, and we have our general solution. Now we care about this for finding eigenvectors of matrices. An eigenvector of a matrix A is a vector V such that AV is lambda V for some scalar lambda. So in other words, the matrix A just stretches that vector V by a particular amount rather than twisting it around. And this value lambda by which the matrix A stretches V is called the corresponding eigenvalue of that eigenvector V. So for example, let's verify that 2, 9 is an eigenvector of this matrix and find the corresponding eigenvalue. So to do this, we'll multiply these two. So this is our AV. And multiplying these, remember that we want to hold 2, 9 over the matrix and metaphorically sprinkle down, where the sprinkling is multiplication, and we add. And computing that, we have 836. And 836 is a scalar multiple of 2, 9. We can pull out the 4, and is the same as 4 times 2, 9. So that's our AV equals lambda V. So we would say that 2, 9 is an eigenvector of this matrix with eigenvalue 4. This is a direction in which the matrix stretches it by 4. And most directions, if you were just plug in a random vector here, you would not get a scalar multiple of the vector that you started with. But this is a special direction where it is a scalar multiple of the original. So given a vector, it's not hard to verify if it's an eigenvector and to find the corresponding eigenvalue. What about the other way though? What about given an eigenvalue, find the eigenvector? So another eigenvalue of this matrix is lambda equals -3. Find the corresponding eigenvector. To do this, we do the following clever algebra. So given an eigenvalue lambda, we want to find a v such that AV is lambda V. What we can do is subtract lambda V from both sides. And now we'll stick an I right there. And remember, the identity matrix doesn't do anything. It's the equivalent of the number 1. And the reason that we're putting it there is that now this is a difference of two matrices, both multiplied by V on the right, so we can factor out the V. And this is a matrix equation where we can then solve for V. So if A has eigenvalue lambda, its corresponding eigenvector satisfies this matrix equation. So here, we want to solve A minus lambda I V equals 0, which is solving this matrix equation, plugging in our lambda and A, which is solving, just simplifying it's that. That's distributing the 3 inside the matrix via matrix scaling, and we have a double negative. And that is the same as solving this. So can we think of a vector where if we multiply this matrix by that vector, we get 0? We can often do this by eyeballing without needing to do any kind of solving. So remember with matrix multiplication, we would tilt and sprinkle. And you think of any numbers that we can put here and here, where when we tilt and sprinkle and add, then we wind up getting 0. If you thought maybe something like just 1 and 1, that is right. When we do this multiplication, then we get 0, 0. I should clarify that when we're writing 0 on the right-hand side here, Sometimes we denote the 0 with an arrow over it to indicate that it's the vector 0. What that really means is 0, 0. So v equals 1, 1 works, and that would be an eigenvector where the eigenvalue lambda equals -3. And you can verify, if you multiply this matrix here by 1, 1, this matrix times 1, 1, when we perform that matrix multiplication, then we wind up with -3, -3, which is indeed -3 times 1, 1, and that verifies it. This verification is not strictly necessary, it's just checking our work. So that is how we can find an eigenvector corresponding to an eigenvalue. You solve this equation, and you can easily eyeball it in the way that we just did, by finding what to tilt and sprinkle to get the desired result. And if you can't eyeball it, once you get to this stage, so we solved this matrix equation, which was this, by eyeballing it and seeing that if we multiply the first column by 1 and also the second column by 1 and added them, then we would get the desired 0. So we found by eyeballing that v equals 1, 1 works, as does any scalar multiple of it. However, if we couldn't eyeball it, then we can solve by hand, because this is the same as solving the augmented matrix, -2, 2, -9, 9 equals 0, 0. Remember, reading off the equations, this is the same as a system of linear equations, which is the same as that augmented matrix. And then one could proceed to do elimination. So we could do row 1 divided by -2 to get a 1 up there where we want it. And then after that, we want to eliminate that -9. So we would do row 2 plus 9 times row 1 and get this. And now we have eliminated above and below every leading entry. We can't eliminate that -1 because there is nothing else. So at this stage, then, just as before, when we were solving systems with infinitely many solutions, we would write out the system. This is x minus y equals 0. And the second equation says that y is free, 0 equals 0. And we write that as x equals y and y equals y. Remember, any free variable, you just say it's equal to itself, which is the same as xy equals yy, pull out the y. And we typically rename y to be t or c. And we get that the solution is any scalar multiple of 1, 1. So eyeballing it, we got a single eigenvector, and we only need 1. So this is fine. But any scalar multiple of an eigenvector is also an eigenvector. So 2, 2 would also work, 33 also works, and so on. So it is for this kind of thing that solving systems with infinitely many solutions is very important. We'll be seeing how exactly soon. Okay, so that's finding eigenvalues for eigenvectors and finding eigenvectors corresponding to eigenvalues. You solve this equation, usually you can just eyeball it. If not, then write out the augmented matrix like this and row reduce and solve. But how do we find one of these from scratch for a given matrix? To do that, we'll need a little bit of theory. First, non-trivial solutions to ax equals 0. Ax equals 0, that is the form of this. It is a matrix times v equals 0. A matrix times x equals 0, just different variable names. And because the matrix A represents a function, it sends a vector x to f of x defined by f of x is ax under matrix multiplication. That means that A is invertible if and only if the function that it represents has an inverse. But a function f has an inverse if and only if it is a 1, 1 function. Therefore, if a matrix is not invertible, then there are two distinct vectors, x and y, that the matrix sends to the same place. This is just saying that the function that it corresponds to sends two different inputs to the same output. But if that's the case, then subtracting ay from both sides, we have this. And then factoring out the a, we have this, but x and y were different inputs. So where v is their difference, that difference is not 0. So that means that if a is not invertible, then there is a non-zero vector v such that av equals 0. And remember that non-invertibility is the same thing as the determinant being equal to 0, because a matrix is invertible if and only if this thing that we're dividing by is not 0. If it is 0, then it is not invertible. And therefore, the determinant of A is equal to 0 if and only if there is a non-zero vector V such that AV equals 0. Because determinant of A being 0, this part means it is not invertible. And if it is not invertible, then it's not 1, 1, which implies that there is a non-zero vector V such that AV is 0. So therefore, there is a non-zero vector V such that A minus lambda IV equals 0, if and only if the determinant of this matrix is 0. So therefore, lambda is an eigenvalue of A, if and only if the determinant of A minus lambda I equals 0. So this is how we can find eigenvalues from scratch for a given matrix. We want to solve for where this determinant equals 0. And remember again, the determinant of a matrix ABCD is AB minus BC, the main diagonal minus the other. So find all eigenvalues of this matrix. So using this theorem, we want to solve for where is the determinant of A minus lambda I equal to 0. Okay, well, writing that out, that's determinant of 6 minus 4, 3 minus 1, minus lambda I is the nice diagonal of 1s, equals 0. Lambda is just a scalar. We scale every entry in the identity matrix by lambda. So this is saying that we want the determinant of 6 minus lambda, minus 4, 3, and negative 1 minus lambda to be equal to 0. Okay, and at this point, we plug this matrix into our determinant formula. So the main diagonal minus the other diagonal, our AD minus BC, the thing boxed up here, would be the following. There is our AD, and then minus BC, which is negative 4 times 3. We want that determinant to be 0. And you can see that we just have a polynomial at this point, a polynomial where we need to solve for lambda. So foiling this out, we have that. And then factoring the result, we have a minus 2 and lambda minus 3. So we find that lambda equals 2 and 3 are the eigenvalues of this matrix. So that is how we find eigenvalues from scratch. We plug into determinant of A minus lambda I equals 0 and do this, and we will wind up with a polynomial where we can then typically factor it and solve for lambda. And at this point, once we have the eigenvalues, then we can find the eigenvectors using what we already learned how to do. So what are the eigenvectors? So we just found that the eigenvalues are 2 and 3. And for each of these, we need to find an eigenvector. So for lambda equals 2, let's find that one first. We want to find a v such that, well, A minus lambda I v equals 0. In this case, writing it out, it's this. So we want to find a v such that this matrix equation is true. Can you think of any numbers that we can sprinkle down on columns 1 and 2 to yield 0 after addition? If you're thinking 1, 1, then indeed that works. When you sprinkle and add, then we indeed get 0, 0. So an eigenvector for lambda equals 2 is 1, 1, and any scalar multiple of it. And similarly, for lambda equals 3, then we want to solve for where A minus lambda I v equals 0. So that is solving this. Can you think of what numbers we can sprinkle down on columns 1 and 2 so that when we add, we get 0? What can we put here? There's no one right answer. If you're thinking maybe 4 and 3, then that's probably the nicest. Doing that multiplication and addition, it does yield 0, 0. So 4, 3 works, or any scalar multiple of it. So if you were thinking, say, 1 and 3/4, then that's also good. Remember that it's an entire direction. The eigenvector is anything in the entire direction that the matrix scales by the eigenvalue. So 1/3 is this vector scaled by 1/4, where we multiplied each entry of this by 1/4. And you can verify that 1 3/4 indeed also works. And there are infinitely many other valid answers too, but in practice, we just need a single eigenvector. So that's our example of finding eigenvalues and eigenvectors of a matrix from scratch. That's how it's done. You first find the eigenvalues by solving for where the determinant of a minus lambda I is 0 and plugging into the determinant formula up here and getting the eigenvalues. And then for each eigenvalue, you find a corresponding eigenvector by plugging into a minus lambda IV equals 0 and finding an appropriate v. Usually doing it by inspection works. If not, then solve the equation with row reduction, as we have done a couple of times now. Now, we'll conclude with finding eigenvalues and eigenvectors of a 3x3 matrix. The principle behind this is the same, except we will need to know how to find the determinant of a 3x3 matrix. So we know that the determinant of a 2x2 matrix, ABCD, is AD, the main diagonal, minus BC, the other diagonal. And the determinant of a 3x3 matrix works as follows. If you have a 3x3 matrix as depicted here, then what you do is you duplicate the first and second columns over here, and then it is the sum of the products of these diagonals minus the sum of the products of these diagonals. And one way to think about this is that when we're looking at a diagonal, it loops around. So once we get to this point, then it loops back to A3, 1. So we can use this to find all eigenvalues and eigenvectors of a 3x3 matrix, and the formula is the same. Recall that the eigenvalues are those that satisfy that the determinant of A minus lambda I equals 0. So we want determinant of A minus lambda I to be equal to 0. And we add these two together. The lambda just distributes to all entries, and it makes so that it's a nice diagonal of lambdas like this after we pull the lambda inside. And then subtracting, this is saying that the determinant of this matrix is 0. And at this point, we can find the determinant of this 3x3 using the method that we just learned. We take the sum of the products of the diagonals. Okay, so here's that main diagonal. The next diagonal goes 1, minus 1, and then it loops around back to 0. So plus 1 times minus 1 times 0. The next diagonal goes 1, and then it loops around to 1 and 1. Remember, taking the diagonals, it just loops around. So 1, 1, 1 is the next diagonal. And we subtract the same thing for the other diagonals going from lower left to upper right. So 0, 5 minus lambda 1. The next is 1, negative 1, and then it loops around to 4 minus lambda. And the next is 3 minus lambda, and then it loops around to 1 and 1. And we want that to be equal to 0. And if one FOILs all of this out, then one will get that this is the same as negative lambda cubed minus 2 lambda squared plus 23 lambda plus 60 equals 0. So I obviously skipped some algebra steps here, but it's just FOILing it all out and writing it as the polynomial that it is. And at this point, we need to solve for what lambda is, and we can do that by factoring this. And this again is tedious algebra. Remember that you can plug in points and find a root and then use polynomial division and factor out terms, and you'll end up getting that this factors in the following way. And therefore, lambda is negative 4, negative 3, and 5 are the eigenvalues. So we got that lambda is negative 4, negative 3, and 5. And now for each of these, we find a corresponding eigenvector. So let's begin with negative 4. What we want is that a minus lambda I v equals 0. Writing it out, it looks like that. And this addition is always simple. Remember, this distributes to the main diagonals, and we're just adding 4 to each of the diagonal entries. So this is the same as saying that we want a vector v such that this matrix times v is 0. So we could row reduce this as we learned how to do for solving undetermined systems. However, if we can do it by spot checking, then all the better. And a trick is that if you have zeros in places, then you can use that to a great advantage in trying to find numbers where when we sprinkle down an add, it ends up being 0. Namely, there's a 0. So no matter what number we put here, when we do the sprinkling and adding, it doesn't affect anything. It's still going to be 0. So because that number doesn't matter, the only way to get rid of that 1 and 1 is with these two. So how can we get rid of a 1 and 1? Well, we can do something like 1 and -1. Then when we sprinkle and add, those go away there, and also those go away. And now the only thing left is to make it so that this second row also yields 0. We have 1 times 9 plus -1 times -1 is 10. So right now, sprinkling and adding, we have a sum of 10 right there. And we want to get rid of that, make it a 0. If it is a sum of 10, we need to multiply this 1 here by -10. So when we sprinkle those, i.e. multiply and add across, then it works. And we have that b equals -10, 1, -1 is an eigenvector for lambda equals -4. Now, in some cases, there won't be zeros, or it might be harder to eyeball and spot find a vector that works. And in that case, we need to solve this equation. So let's illustrate how we would go about solving this equation. Okay, so for lambda equals -4, we got this. And if we couldn't eyeball what a appropriate v is, then we would do the following. Write out the augmented matrix for this. Remember, it's equivalent to a system of equations. This is 0x plus 1y plus 1z equals 0, and so on. And we want to solve this matrix equation. So we want a 1 in the upper left. First thing to do would be to swap rows 1 and 2, which is the same as writing the equations in a different order. And then we eliminate below the top left entry. And those are already eliminated, so we don't need to do anything. So then we eliminate that guy. And we can do that by doing row 3 minus row 2. And that entirely eliminates row 3. That means that we have infinitely many solutions, which we will always have for solving for eigenvectors, because it's an entire direction that's being stretched by the eigenvalue. And then we want to eliminate above this leading non-zero entry, we want to eliminate that 9. Remember, we can't eliminate these guys because there's no 1 there that we can use to eliminate them. We only eliminate above and below the leading non-zero entries. So to eliminate that 9, we want to use that 1. How can we do that? Well, row 1 minus 9 times row 2 does the trick. Then we have 9 minus 9. And we have a 1, 9 minus 9 is 0, -1 minus 9 is -10. And at this point, we are done, because we have eliminated above and below all the leading non-zero entries. And when we're done, then we write out the corresponding equations. The first row says x minus 10z equals 0. Second row says y plus z equals 0. And the third row says that z is free, i.e. z equals z. No constraint on z, you write z equals z. And that is the same as x, y, z is 10z, -z, and z. Moving these to the other side. And then we just pull out the scalar z. And the solution is that it's any multiple of 10, -1, and 1. When we did it by eyeballing it, we got -10, 1, and -1. But that's in the same direction as this. The z can be any constant. So if z is -1, then that -1 scales all components, and we get what we got by hand. And I should emphasize that both are eigenvectors, and we'll only want one eigenvector. We'll end up incorporating for the scaling with arbitrary constants anyway, so it doesn't matter. Either of these will be perfectly good choices. Yeah, so if you can't eyeball it, you can always do this. It always works. Although if you can eyeball it, that's obviously faster. Okay, so we got that lambda was -4, -3, and 5 were our eigenvalues. We just found a corresponding eigenvector for -4 in two ways. Let's move on to -3. As always, we want to solve a minus lambda I b equals 0. So that is the equation we want to find. Now, if we're doing such things by hand, remember to always look for zeros, because that means that for eliminating like this last row, it does not matter what numbers we put here and here. They have no effect on anything. No matter what they are, they'll be 0. The only way to put any numbers up here so that when we distribute and add, we end up with a 0 is if this middle number is 0. That's the only way when we sprinkle and add that we end up making it so that the third row is 0. And now that we know that that has to be 0, it makes our job a lot easier. What numbers can we put here and here to finish eliminating for the first and second rows? Can you see it? Yes, something like 1 and 1 work. When we sprinkle, multiply, and add, then this yields that we get 0, 0, 0 across. So pay attention to that very first thing that we did, realizing that the middle one had to be 0 because of those. That first step is crucial. Once you have one number, then it becomes much easier to find the other two. And again, if we couldn't eyeball it like this, then you can always do what we did over here and manually solve the system, and you'll end up getting the solution. And our last one was lambda equals 5. So I encourage you to pause the video and try on your own to find an eigenvector corresponding to lambda equals 5. So writing out a minus lambda iv equals 0, it's this. We are subtracting 5 from each diagonal entry, and the corresponding equation is that. And if you didn't pause the video, I certainly encourage you to pause now and see if you can find, either by eyeballing or this technique, numbers that you can put here to make it so that we have a solution. And remember to keep out for the zeros. That's how to start. So looking at this, we see this 0 right there. And that means that it does not matter what number we put here as far as row 2 is concerned. It will always go away anyway. So the only way to eliminate row 2 would be for this 1 and -1 to go away on their own, which we can do by putting just 1 and 1 there. Then 1 times 1 plus 1 times -1 goes away, and it doesn't matter what that is, it'll go away anyway. And now that we know that that has to be a 1 and 1, now we find a number that works here for the other rows. So 1 times -9 plus 1 times 1 is -8. We want 0, so we have a -8 plus 8 would go away. So 1 times -9 plus 8 times 1 plus 1 times 1 goes away. It works with the second row, and it also works with the third row. 1 times 0 plus 8 times 1 plus 1 times -8 goes away. So in total, we have found that we have eigenvalues of lambda equals -4, -3, and 5, with corresponding eigenvectors of 10, -1, 1, 1, 0, 1, and 1, 8, 1, or any scalar multiple of these. There are infinitely many eigenvectors for each eigenvalue, but it's kind of an entire direction. So any scalar multiple of this would also work. So -10, 1, -1 also works over here. 3, 0, 3 would also work. You can always scale an eigenvector and get another one. So that concludes our linear algebra prerequisite video. And now we can finally begin chapter 8 on linear systems of differential equations. Have a great one.